Welcome to Empowered Learning. This video will be about the study of a concept called vectors. And so what we're going to do is break this up into a two-part series. This first video will be about just the basics, the concepts and theory behind vectors. The next video that I will do, that video will actually go over example problems. So for those of you that kind of already know about what vectors are and some of their basic properties, you can skip this video and go ahead to the part 2 video where I'll go over examples. For those of you that are not familiar with everything in terms of vectors, you may want to watch this video as it may bring some perspective as to what you're going to be doing with them. Also, for those of you that do know about vectors, but you want, I guess, a different perspective or a deeper understanding of what they are and how they work, you may want to watch this video as well. So what we're going to cover here is first what the definition of what a general vector is going to be, and to try to understand what vectors are conceptually. So, and the reason I say it like that is because this whole idea of having vectors and creating math to go around using them comes from some kind of motivating factor, a motivating concept, and we're going to talk about that. Okay. We also want to be able to discern in between the different types of vectors that we have. Okay, and the ones that we'll deal with here is just mainly a regular or standard vector, a position vector, a displacement vector, a component vector, and a vector in standard position. So we want to see the similarities and differences in between those. We do have other types of vectors, but I will cover that in later videos where I may do some of that in my dot product and cross product videos just to kind of round that out. So the basic rules and properties of vectors, we're going to talk about what does it mean to have two vectors that are equal. We're going to review what scalar multiplication and vector addition looks like. We're also going to go deeper into the vector addition because the way that vectors are added kind of follows the Parallelogram Law, and we'll talk about what that is in terms of the length of a resultant vector. Okay. And then, of course, we'll talk about breaking down vectors into what we call their components. And we're specifically going to talk about horizontal and vertical components. And of course, before we talk about that, we do need to talk about the concept of a unit vector, because a unit vector is fundamental in being able to let us know the direction that a vector is in. So that's an important concept as well. So usually when we model or solve problems that deal with quantities like length, area, volume, temperature, or time, we know that these quantities can be characterized by just a single real number. Okay, so in other words, it's just a number. There's nothing else that's implied that goes with it. However, when we start to talk about concepts like velocity, acceleration, force, when we think of those things, that is an implied quantity, but in a direction. Okay. And so because of that, vectors, the motivation for vectors is to say, all right, well, how do we deal with this concept of a certain magnitude or a certain force or a certain amount of something going in a particular direction? Okay. That's different than just saying, hey, I have the number 2 or the number 3, or even, let's say, the complex number 3 minus I. Okay. So this concept of an actual quantity going in a certain direction is something that we need to look at. And so that's really the motivating factor for coming up with what we call vector algebra here. Okay. So as I state here, in short, we will see that vectors are nothing more than our attempt as humans to quantify and understand quantities that have some implied direction to them. Okay. So in the world of vectors, we call single real number quantities scalar numbers. Okay. And so this is one of the things that we need to know in in the world of vectors, there is a different jargon or a different set of words that we use, or vocabulary that we use. And so we don't really call real numbers in the vector world. We call them scalars. Okay. Now, we call real number quantities that have an implied direction to them vector quantities. And so, of course, that's the difference between a scalar and a vector. Scalar is just a real number. A vector is a real number with some kind of implied direction to it. Okay. Now, vector quantities are composed of magnitude and direction, and we usually characterize a direction by some angle. Okay. And that angle could be anywhere from 0 right up to 360 degrees. We don't actually include 360 degrees because, of course, that's the same as 0 degrees. Okay. And so actually there should be a degree symbol here. But in radians, of course, that will go from 0 all the way up to, but not exactly to pi. Okay. And so that is our way of being able to sort of conceptualize, quantify what a direction will be. We use angles for that. Now, when we talk about the basic definition for a vector in its most simplest terms is just a directed line segment. And it begins at some initial point, ends at some terminal point. Okay. So like you see here in figure 1, my vector AB, and you'll see that one of the ways that I'll denote that, or the way that I'll do it in this video, is this way. A lot of times you'll see in textbooks, because of the difference in between bold print and regular print, they'll make all the vectors bold and make everything that's not a vector not bold. Okay. But here, since I'm kind of writing this out, we can't really see the difference in between that. Oh, well, we could, but that would take a long time to write. So I just do the arrows. Okay. So we see here that vector AB starts at A, ends at B. Okay. Vector AC starts at A, ends at C. And we see here that vector AC has an implied direction of 57 degrees, and that is from the positive x-axis. So that 57 degrees is an angle in standard position. And of course, vector AB is in the direction of 110 degrees via an angle in standard position. Okay. Now, of course, down here in this note, I'm just basically saying that I'm going to be using the arrow convention versus the bold convention here. Now, I've already mentioned here that my vector AB is going to be some vector in this direction. But notice for this particular example that the magnitude of the vector, or what we call the length of the vector, is going to be 40 meters per second in this case. And so, of course, for vector AC, that length of that vector is synonymous to 60 meters per second. Okay. And so another thing that I need to mention here is I've done it here, but it's not necessary that you do this all the time. Notice that the vector AB is shorter than the vector AC. Okay? And normally we will say, all right, vectors that are longer have a bigger quantity to them for what it is that they're trying to represent. And we normally draw them longer, but it is not necessary to do that all the time. In other words, it's not necessary to have it drawn to scale. Okay. If you want to be exact, you can, but the main idea is that, hey, one vector's length or magnitude is going to be bigger than the other, and that's the most important thing. So I don't have to draw this vector here, the AC. I don't have to draw it to where it's this length is actually 20 more than this one. Okay, so that's not really necessary. All right, so now we're going to talk about the types of vectors. And the reason I'm going through this is because if you read through textbooks, or let's say you do searches online or whatnot, you'll see people talking about all these different kinds of vectors, but there, at least for me, there is no one place that kind of says, all right, well, for what we're going to be talking about in the scope of this particular video, what are all the possible vectors I could possibly deal with? Okay. Of course, in the dot product and cross product videos, I'll talk about other vectors there, but for like the basic ones, I wanted to put one place where you can kind of have a little vocabulary sheet to know, all right, well, when someone says this kind of vector versus that kind of vector, what do they mean? Okay. And we'll see that some of these vectors, vector names are really the same thing. They just have alternative names for it. Okay. So a general vector is the same definition that we stated previously. Okay. And that was just a directed line segment where it starts at some initial point and it ends at some terminal point. Okay. Now, a position vector is a vector that has an initial point that is fixed, meaning that this point will not move, but the terminal point here is one that can possibly move. Okay. Doesn't have to, but normally when we talk about a position vector, we're assuming that that terminal point is actually moving, and it may be moving with, let's say, time. Okay. Now, if we want to think about this from a practical standpoint, let's say where a car is starting to move and it starts at point A. Okay. And then let's say 2 seconds from now, it is traveling at 20 meters per second. Okay. And then after that, let's say the car after that is going to be traveling at 30 meters per second. Okay. It looks like this. So my point here is that with this traveling 20 meters per second, it's traveling 20 meters per second in a certain direction. Okay. And so whenever I look at the second vector here, so this is where it started, this is where it finishes. So what you can think of this as is my car is going 20 meters per second in this one direction. And when I track what its speed is again, it may have turned, let's say, 20 degrees to the right or something like that. So to where it's following the straight path from where you originally started, and now it's traveling at 30 meters per second. So that's a way that you can sort of think about that. The main thing here is that a position vector, this terminal point here is expected to move. Okay. But of course this initial point is not. That's the main thing. Okay. Now, a displacement vector is a vector that represents the change in the initial to final position of some other position vector. Okay. So in this example here, you see that vector AB is going to be the position vector at its initial position, and vector AC is going to be that same vector, but now at a different position. And of course, vector BC that is here is what we call the displacement vector. So the vector that goes from where our position vector first started to where it ends. Okay. And so I think the easiest way to see that is just the picture here. All right. So for a component vector is a special kind of position vector whose initial fixed point is at the origin in a Cartesian or rectangular coordinate system. Okay. So the only difference in between a regular position vector and a component vector is that the initial point for a component vector is always going to be the origin. Okay. And if you're in 2D space, that would be the point 0, 0. If you're in 3D space, that would be the point 0, 0, 0. For those of you that know about tensors, which is just basically vectors that are what is basically vectors, period. But people don't really call them tensors unless you're in, let's say, 4D and higher space. So let's say we had a tensor, let's say of rank 4 or whatever. Okay. then it would look like this, okay? All right. So a standard vector, or a vector in standard position, as it's called, is actually just a formal name for a component vector. So a component vector and a vector in standard position are essentially the same thing, okay? When we say a vector in standard position, we're just being a little bit more descriptive so that we can know that we're starting here at the origin, okay? Now, another thing that I want to mention here is that there is a difference in between having a component vector versus a vector being expressed in terms of its components, okay? That is totally different, okay? And so as we get later into this video, we'll actually see what it means to have a vector, whether it's a vector in standard position, whether it's a position vector, whether it's a displacement vector. We'll see what that looks like when we break that particular vector up into components, okay? Now, again, this is just my note basically saying what the origin will look like, or the initial point will look like in 2D space versus 3D space, okay? And so this vector here, when I do something like this, this is a vector being expressed in terms of its components, okay? And so we're going to find out later how to actually calculate those, but when we write it like this, it is assumed that when we write it like this, we have some vector and we've expressed it in terms of its components. All right, and of course, I just repeat that. So now let's move on. Now, when we talk about the magnitude of a vector, what we're really saying is, if we're looking at it on paper, how long is the vector, okay? In reality, what we're doing is trying to put a real number quantity to that velocity or acceleration or force that's going in a certain direction. And so we look at the two things separately. So we look at, all right, well, how much is this quantity, or velocity, acceleration, force, field, whatever? How much is it, and in what direction it's going? So the magnitude takes care of the how much is it part, okay? And so simply put, the way that we calculate the magnitude of a vector is we essentially use the formula that's better known as Pythagorean's theorem, but it's really not Pythagorean's theorem because Pythagoras didn't make it up. But let's say if we took a general vector like this, and this vector could be composed of a component that's, let's say, on the x-axis, another component that's going to be on the y-axis there. And this vector component that's on the x-axis, it could actually have its own magnitude, okay? And that doesn't look too nice, but I'll try to redraw that. So this should be like V1 in this direction, and then the magnitude of that. And that's essentially what this particular part would be, okay? We would just call it V1. And of course, we got the same thing going here in the Y direction. And I'll formally talk about this later, but I wanted to go ahead and say this now because these are just essentially the components of the vector that we're dealing with. And the point that I'm trying to make is that if we look at this particular vector here from, let's say, this point to this point, it forms a right triangle. And we know that the relationship in between the sides of a right triangle is that this side squared plus this side squared equals to that side squared. And we're just talking about lengths. So if we say, hey, v squared is equal to v1 squared plus v2 squared, and then take the square root of that, v here by itself is going to be represented as a length, okay? Since we want to be formal, we know that we're talking about vectors, we just use the notation of absolute value of the vector to represent its length or its magnitude. Okay. Now, this is what it looks like in 2D space. This is what it looks like in 3D space. Okay. And essentially, it is the same thing. Okay. In 3D space, we're looking at this part here as the length of the resultant of the X and Y components, if you want to think about it that way, and then we just add on the Z here. Okay. There's a little bit more to it than that, but for the sake of trying to keep it simple, that's what's most important. Okay. So now that you know that we can find out the magnitude just by basically squaring all the components, adding them up, and then taking the square root of that final result. That's how we end up getting the magnitude of the vector. Now, the formula that I showed you is what it looks like if we're dealing with a component vector, meaning that our initial point for our vector is at the origin. If we're dealing with a position vector that is not a component vector, then of course we have to take, well, what is going to be the distance in between those 2 points in the X direction, the Y direction, and the Z direction. And so because of that, we see that our formula for magnitude is just going to be the difference in between the X coordinates plus the difference in between the Y coordinates. Well, the difference in between the X coordinates squared plus the difference in between the Y coordinates squared plus the difference in between the difference in the Z coordinates squared, and then we just square root all that if we're in 3D space. Of course, for 2D space, we only have to deal with the X's and the Y's. Okay. All right, so now that we know what a vector is from a conceptual standpoint, and we know how to categorize the different types of vectors, now what we need to do is figure out, well, how do we work with these vectors? Okay, so it's just like when you were in grade school, the first thing that you learned about are numbers. You learn how much 1 is, you learn how much 2 is. Okay. And then the next thing that you learned is, all right, well, now that I know what 1, 2, 3, 4, 5, 6, and all that stuff is, what is the whole concept of saying, if I take 2 and add it to 3, what do I get? Okay. If I was to take 5 and subtract 6 from it, what do I get? And what does that mean? So analogously, in the world of vectors, that is what we're about to do now. So we're about to go over some basic rules to let us know, all right, when you work with these elements called vectors, what can you expect? Okay. So the first thing is we need to know when 2 vectors are equal to each other versus when they're not equal to one another. Okay. So any 2 vectors that are equal, they'll have the same magnitude and direction. So if we're drawing those 2 vectors that are equal, they'll be the same length, and at worst, they'll be parallel to each other. So for instance, vector A and vector E are considered to be equal vectors because they both have the same length and they both have the same direction angle. Okay. Now, it is not necessary for vectors to lie on top of each other to be equal to one another. Okay. All they have to have is the same magnitude and the same direction angle. That's it. We can have one vector, that's over here and another vector that's way over here. Okay. If they both have the same magnitude and direction angle, then they're considered to be equal no matter where they're placed. Okay. All right. So vectors that have either different magnitudes and or different directions are considered to be non-equal vectors. So in other words, it's like an all or nothing thing. Okay. If your direction angle is the same, but your magnitude is different, the vectors can't be equal. Okay. As vice versa is true, the vectors can't be equal. And so if we look at examples here, we see that vectors A and B are equal, but we see that vectors B and C are not equal. Matter of fact, they're opposites of one another. They have the same they have the same length, but their direction angle is exactly 180 degrees apart from each other. That's because they point in exactly the opposite direction. Vectors B, C, and D, of course, are all different from each other because none of these vectors share both the same magnitude and the same direction angle. Okay. All right, so let's move on. So now we need to talk about scalar multiplication and addition of vectors. And so when we say scalar multiplication, remember, all that we're saying here is that we're saying, how do I deal with doing real number multiplication when I'm dealing with vectors? And when I'm talking about addition here, I'm actually talking about vector addition. So we want to make sure that that's clear. Okay. So here, if we have some real numbered value that we call a scalar being multiplied like how we multiply with regular real numbers to a vector, then we can denote that vector as just that real number times the vector with the arrow just over the name of the actual vector itself, or we can put the arrow over the entire thing. Doesn't matter. Both conventions are acceptable. Okay. Now, whatever this value, this real number value is, the magnitude of it is going to be the absolute value of it. And so that's because when we look at magnitude, we really don't care about the direction in which the magnitude is. Okay. We know if there's a force going due east, and then that force switches and go due west, the force is still the same. Okay. The direction of it is different, but the actual force itself is still the same. Okay. So looking at that, how we actually interpret this particular vector here is that it's essentially this vector A, but it's going to be increased by a magnitude of k times. So basically, whatever the magnitude of this particular vector is, if we multiply that times k, that is going to be the magnitude of the new vector ka. Okay. So in other words, if the magnitude of some vector is this, and I want to figure out, well, what's going to be the magnitude of this vector, where it's just going to be k time. Oh, sorry. I wrote that in the wrong spot. So it'll essentially just be k times whatever that magnitude is. Okay. So in figure 4 here, what I'm trying to do here is just basically show what happens if I take some vector A and I start to multiply it times some scalar constant value. Okay. So of course, here's my original vector A. If I multiply that vector by a scalar -1, then the vector will now look like this. If I multiply by a scalar of +2, then of course, this vector 2A will be twice as long as vector A. And of course, if I multiply that original vector here by 1/2, then it's going to be half the length of this particular vector. Okay. And if I multiply by -1/2, it's going to be half the length of A and pointing in the opposite direction. Okay. So wanted to make sure that I'm clear on that before we move forward. So in general, anytime we take a vector and we multiply it by a positive scalar, it's going to point in the same direction as the original vector. Anytime that we multiply a vector by a negative scalar, is going to point in the opposite direction. And so what that actually means is, in terms of degrees, it will be exactly 180 degrees in direction from where the original vector was pointing. And of course, if that scalar value is 0, then what that reduces to is what we call the 0 vector. Okay. And the 0 vector is a vector that has neither magnitude nor direction. Okay. And of course, the 0 vector, depending upon what dimension you're in, looks different. If we're talking about in 2D is going to look like this. If we're talking about 3D, it's going to look like that. Of course, if we were talking about 4D or 5-dimension space, then we would have 4 or 5 components where all of them will be 0 according. Now, in the world of vectors, this 0 vector thing that I just talked about, it plays a similar role to how 0 actually plays a role as what we call an identity element within the real numbers, okay? So just like you know that if I take any real number and add it to 0, I get that real number back. I call that the mirror property of it. If I take any number and I add it to the opposite of itself, I always get 0. And if I take 0 times any real number, I get 0. My point here is that when we talk about vectors, the 0 vector acts in the same way as the number 0 acts within the real number set with addition and multiplication as its operations, okay? Or for that particular, as math people call it, that particular algebra system, okay? So this 0 vector acts the same way. So if A is a vector, and this is that, then it's just going to give me the A vector back again. If I add a vector A to the opposite of itself, it's going to give me the 0 vector. And if I have the 0 vector multiplied by this particular vector here, even though we haven't talked about this because we'll cover that in the dot product, what it'll actually end up being is still being the 0 vector, okay? And so again, the concept of 2 vectors being able to be multiplied times each other, that has a lot packed into that. And so I would have to probably define what the dot product is first to be able to really talk about this. But my point is, I'm just going ahead and telling you now that this particular 0 vector acts just like the number 0 within the real number set, with addition and multiplication being the primary operations, okay? All right, so let's move forward here. So anytime we want to take 2 vectors and let's say we want to add those 2 vectors together, and particularly, even though I didn't write it here, we are talking about non-zero vectors. We see that the way that vectors add up isn't necessarily the same way as if we were taking 2 numbers within the real number set and adding them up. They just don't work that way, okay? So we know that in the vector world, if I wanted to take the sum of 2 vectors A and B, the resulting vector would be a vector with the magnitude equal to the length of the diagonal that's created by making this 2-dimensional parallelogram here, okay? And of course, it will have its own special direction angle as well, okay? So it won't have the direction angle of A, it won't have the direction angle of B. In this case, it'll be something in the middle, okay? But we would have to go deeper into that to figure out exactly what it would be, okay? Right now, we're not going to focus on that. If you watch my dot product and cross product videos, then you'll actually see how we can figure out that actual the direction angle, okay? But for right now, the main thing to know is that the length of this, what we call a resultant vector, or the sum of these 2 vectors here, will be the length of this diagonal, okay? It is not directly just whatever the magnitude of this is plus the magnitude of that, okay? So that's the main point there. And so, of course, this phenomenon is known as the Parallelogram Law. We also see here that in figure 5b, one of the things that we know is that if I take 2 vectors, let's say I take a vector A and a vector B and I add them together, if I was to take the vector A and then build it onto the vector B to get that result, it's the same thing as taking the vector B and building it to get the vector A. And so I'm going to display that or demonstrate that now. So I'm going to switch colors here. So if I wanted to do A plus B, then what I would do is I would start at this point and I would draw vector A. And then after that, I would take vector B, which is here. And notice that as long as a vector has the same direction, angle, and magnitude, it is equal. So I can draw an equal vector B here. And I would just say, all right, well, I started here, I finished here, and I connect the two from start to finish to get that resultant. Okay. And so that would be what that vector is. Now, if I started and said B plus A and formed that vector, then this would be your vector B. The equivalent vector for vector A over here could be drawn here. And of course, it'll be the same length in the same direction, okay? So we know that. This figure B here also shows us that if we want the negative of vector A plus B, then that's just going to be the same vector, but in the exact opposite direction, okay? And figure 5C shows us what it looks like whenever we not only add, but subtract vectors, okay? And so whenever we subtract vectors, just like how it is in whenever we're dealing with the real numbers here, let me erase this. So we're going to switch back to black, well, blue here. Yeah, so just like how we would say A minus B with scalar numbers is A plus a minus B. Well, we do the same thing with vectors, but realize that A minus B in terms of vectors is saying, hey, I want to look at the vector A, and then I want to add a vector B to it that is in exact opposite direction of what vector B is. So as you can see, vector B is here, but vector minus B, I could draw that like that, okay? And so if I was to take a vector minus B and then a vector A and build those onto each other to be able to come up with a resultant vector, then it's going to look something like this. So this will be the vector minus B. This will be the vector A. So we'll have minus B plus the A, and that will be the same thing as A plus the minus B, like that. And of course, that would be just the vector A minus B, like that. And so dealing with subtracting vectors here, just kind of what I just went through, we see that the vector of A minus B with the big arrow all over it is the same as just a vector A plus vector B going in the opposite direction of what B originally was. And of course, here, if we take a vector A and add a vector that's in the exact opposite direction to it, we end up getting the zero vector. All right, so now what we need to do is go over the summary of all the properties that we can talk about right now with vector operations. And so this excludes those vector operations like the dot product and the cross product. And I'm going to explain why that is here. We're just dealing with the vectors that have scalar multiplication and vector addition with it, okay? That's all we're dealing with. When we start to talk about the dot product and the cross product, those are two totally different concepts, and they have their own set of vector operations that goes with those. So if we were considering that we have these three vectors, u, v, and w, and we had two real number values, scalar values, a and b, then we know that vectors act in a way to where they are commutative under vector addition. What that basically means here is that vector u plus vector v is going to be the same thing as vector v plus vector u. And we've seen that already, okay? And so why it's important for us to know the properties that I'm going to talk about here is that we're kind of comparing everything to the algebra system or the set of elements that we're all familiar with working with, which are the real numbers, okay? So we always do this comparison of saying, well, hey, now that we have these elements, how does everything work? Okay. Do things work similar to what they do within, the real number set using addition and multiplication as the operations, or are they a little bit different? Okay. And so we see here that with vectors, the commutative property of addition, it works the same way as it does in the real numbers. So just like 2 plus 3 is the same as 3 plus 2 in real numbers, if we have two vectors and we add them up, we can switch them around and it ends up being the same thing, okay? We've already discussed that anytime we add a vector to the zero vector, we just get that original vector back, okay? And so we see here that the zero vector is acting as an identity element, okay? And of course, if you do an operation with the vector, you get the same thing back. These two vectors, u and u, are identical. So that's why we call it that. All right, we see here that in terms of multiplication, any vector being multiplied by a scalar value 0 is going to produce the zero vector, okay? And again, that acts very similar to how it does in the real number set, okay? The associative property for addition also holds. So just like within the real numbers, if we had 1 plus 2 plus 3, and I wanted to add 1 plus 2 first, or if I wanted to add 2 plus 3 first, I would still get the same quantity at the end. Well, if we do that with vectors, we're still going to get the same vector at the end, regardless of whether we want to combine u and v first or v and w first, okay? Again, we see here that anytime we add a vector to its opposite, is always going to produce the zero vector, okay? And that's another trait of the identity element for a particular algebra system, okay? And we see that this set of vectors under addition and multiplication, that still holds. We also see here that if we multiply the scalar 1 times a vector, we end up getting that original vector back. And so what this is actually telling us is that this value 1 here, 1 is what we call the identity element for the real numbers under the operation of multiplication. And we know that because anytime we take a real number multiplied times 1, we get that original number back. Just like 0 is the identity element for addition, okay? So whenever we add numbers and we want the thing that we started with back, we would use 0. If we're multiplying, we would use 1. And so this property is just basically saying that if I was to use this scalar just like this, this property under the real number still holds for vectors, okay? Now, we don't really get into the whole thing of there is a 1 vector or a 2 vector, okay? So we don't necessarily have a vector here where, all of its components are 1s. We don't really call that a 1 vector or a 2 vector. We could, but we just really don't do that, okay? All right, so rule number 7 here basically says that if I have some constant multiple of a vector and then I multiply it times a scalar value, that's the same thing as if I was to multiply both of the scalars together and then multiply that scalar times the actual vector. Now, what this is actually saying here is that the associative property of, this is like a version of the associative property of multiplication with vectors. Okay. Now, the thing is that this is not a true associative property, because a true associative property with vectors would be like this. Okay. And so the thing with vectors is the whole concept of taking a vector and multiplying it together is something that has a little more going on with it than just saying, hey, I'm just going to multiply these two things together, and it's going to act like repetitive addition does within the real number set. This is not the same thing. Okay. So what we're saying here for rule number 7 is that the scalar components, that part will keep its whole associative property under regular real number multiplication. That part will stay true, but we can't necessarily say if I have two vectors, we'll say 3 vectors, and I wanted to multiply 2 of them first and then multiply another one, that's going to all act, nice, just like how it would in the real numbers. That doesn't hold. Okay. And so the reason for that is that we don't have a vector property that says that we can do this directly. Okay. Or that vectors act like this. Now, in the vector world, this concept of multiplication has 2 different, what I call, flavors to it, because whenever we multiply a vector to another vector in the vector world, there's actually multiple things going on. So one of the things that's going on is that the magnitude of those vectors are affected. So if I was to take, let's say, these 2 vectors here, let's call them u and v, and I was to, say, multiply them, the magnitude of this vector is going to affect this vector in a certain way, and vice versa. The magnitude of the vector v is going to affect the magnitude of vector u in a certain way. Okay, so there's a magnitude aspect to it that we need to account for. But the thing with vectors is that we also have a rotational aspect to it as well that we need to account for. And whenever we quote unquote multiply 2 vectors together, we actually have that magnitude effect and the rotational effect happening simultaneously. Okay. And so we do not have an operation that can kind of quantify both of those phenomena happening simultaneously in the same operation. So what we do is we separate the magnitude effects from the rotational effects. And the magnitude effects, we deal with the form of multiplication that we call a dot product. Okay. The rotational effects, we deal with what we call an operation called cross product. And so that's why I have been mentioning dot product and cross product before, because that's where those 2 operations actually fit within the grand scheme of things. Okay. So that's why we will have our own separate videos on cross product and dot product. Okay. Now, if we talk about, if we go to rule number 8 here and we talk about the distributive property. Now, of course, we're talking about the distributive property of scalar multiplication being able to be carried over vector addition. That works coming from the left and the right. And we also see that if we have 2 scalars being added together, and then we do what we call scalar multiplication with this vector across from right to left, that will also hold. Okay. So it's not exactly the same as the distributive property of multiplication over addition within the real numbers, but with the mix of having a scalar quantity and a vector quantity together and trying to do the distributive property, rules 8 and 9 is how that actually works. Okay. So my note here is just basically saying that it's not one of the things that's not assumed is that the distributive property going from left to right and going from right to left will actually work. And or if we can take, like in this instance, we'll take two vectors and multiply, distribute a scalar over it, versus here we take two scalars and we distribute a vector over it. Okay, and so that's really what these two rules are trying to differentiate. What does it look like when I take a scalar number and distribute it over a vector addition, versus I take a vector with scalar multiplication and I distribute it over two scalars that are being added together. And we see that what's happening here is actually something that is special, and we don't assume that this is going to work exactly like the real numbers do. So whenever we get into a situation where we see something different like that, we want to notate it. And so that's why rules number 8 and 9 are stated explicitly. So now we need to learn about unit vectors, what they are and how we interpret them. So if we're given that we have some vector v that we see here, and we wanted a corresponding unit vector for that, what we essentially do is we take the vector and just divide it by the magnitude of that particular vector. Okay. Now, the reason why the unit vector is special is because it lets us know in what I like to call vector language, what is the direction of that particular vector. To be specific, if our vector is composed of components that are, let's say, on the x-axis, y-axis, and z-axis, that vector will say, well, how much do you have to go on the x-axis, and how much do you have to go on the y-axis, and how much do you have to go on the z-axis to be able to have a vector length of magnitude 1. Okay. So if we wanted to look at our vector that we're looking at in, let's say, in terms of cutting it up into units of 1, the unit vector is the vector that does that. So that's a way of looking at it. Now, in saying that, note that one important property that is true for all unit vectors is that the magnitude of a unit vector will always equal 1. And so that's why I said, when I use the analogy of, hey, how much do I have to go in the x direction, y direction, and z direction to form this particular vector? And that vector is going to be a length of 1, because all unit vectors are going to have a length of 1. And if we move forward here, we know, again, that the direction of a vector v can be described or translated as a resultant vector of length 1, okay, whose components can be used in linear combinations to describe any vector with scalar a times that vector v, such that any vector that's going to be a constant multiple of this vector v is going to lie in the same path as vector v. In other words, they're going to have the same directional angle, and they're going to be laying on top of each other or shooting through one another. Okay, you can look at it that way. So as an example to show you how this works here, let's say we have a vector in component form, and this vector has I will call it a x component of 1 and a y component of square root of 3. So if I find the corresponding unit vector for this, then I see that I just take the vector and divide it by its magnitude, or just say 1 over the magnitude times the vector. All of this just ends up being 1/2. And so I multiply 1/2 that scalar times each of the components of this vector, and I end up getting the component vector 1/2 square root of 3 over 2. Okay, so what I'm saying here is that any vector, scalar multiple of this particular vector here, can be expressed as a linear combination of this unit vector, okay? And whatever vector I have is going to point in the same direction as this particular unit vector, okay? Now, now another thing that's important here is that if I'm looking at my vector itself and I want to rewrite my vector in terms of the unit vector, then I could rewrite it as A times the unit vector, where A is actually going to be the length of whatever vector that is. Now, to put that in another way, essentially the length of a vector is going to be the magnitude of it. So I could express A as basically being the magnitude of V. So because of that, I could basically say that V could be expressed as its magnitude, scalar multiplication times the vector itself over its magnitude, okay? Now, of course, that makes sense because we got this scalar magnitude of V here and that magnitude of V there. Of course, that will reduce to 1 and just give us the vector V left. But here, this is expressed in terms of length and direction, okay? So, and that's a skill that it's important to have, to be able to take a vector and sort of decompose it into its length and its directional vector, or the unit vector, okay? All right, so an example of showing you that I can have some vector V and I can express a non-zero multiple of that vector in terms of the unit vector is going to be this first example here. And I'm going to get rid of the stuff that I've written right here so that we can see that. And then we'll actually look at an example where we take the vector itself and rewrite it as a linear combination of the unit vector. So here, if I let A be 3, then that means that A times the vector V is going to be 3V, which is just going to be 3 times the original vector that I had in component form. And notice, to get 1/2 out of 1, I'm going to have to rewrite 1 as 2 times 1/2. And to get square root of 3 over 2 out of square root of 3, I'm going to have to rewrite that as 2 times square root of 3 over 2. And since I have a common factor of 2 here, I know that I can factor out that 2. Once I do that, then of course 2 times 3 is 6. And now what I have is my vector 3V expressed as the scalar 6 times the component, well, not the component, but the unit vector 1/2 square root of 3 over 2. Okay, which is basically the same thing as this scalar times the unit vector. Okay, so my point here is that I was able to express this vector in terms of the corresponding unit vector for V. Okay, now if I wanted to take the actual vector itself, that would be a case when A is equal to 1. So if I wanted to take the actual vector itself, of course, if 1 is here, 1 times the scalar 1 times the vector is just that vector. If I take that, in order to get, of course, 1/2 here, still got to rewrite that as 2 times 1/2. In order to get square root of 3 here, still got to rewrite that as 2 times square root of 3 over 2. And of course, now I see that my actual vector, V, can be expressed as 2 times the unit vector, okay? And again, I was able to express the vector itself as a linear combination of its unit vector. Now, notice that in both instances here, in this particular instance, that the unit vector, if I go actually calculate the magnitude for that, we see that it ends up being 1. And that's something that must always be true about unit vectors. Okay. Now, we know it's common to use what's called the I vector, J vector, and K directional vector as a unit vector to describe a particular vector in terms of its components according to the X, Y, and Z axes, or if we say it more formally, the X, Y, and Z directions. Okay. And so we define our I vector to be in component form in 2D space. It'll just be 1, 0. In 3D space, it'll be 1, 0, 0. And of course, our J directional vector in the direction of the y-axis will be 0, 1 in 2D space, 0, 1, 0 in 3D space. And then, of course, for our K, that will only be used in 3D space, and that will be 0, 0, 1. And notice for all three of these vector types, whether it's in 2D space or 3D space, if we were to take the magnitude of all of those, we would still end up getting 1. Okay, so it does. So the I, J, and K directional vectors do actually satisfy that particular property. So when a vector is defined in terms of the Cartesian or the rectangular coordinate system, we know it's customary to write out this vector in algebraic form. Okay, so for instance, instead of writing it like this, what we would do is write it like this if we were in 2D space. So we just say the magnitude of the vector going in the x direction times the I directional vector plus the magnitude of that vector going in the y direction times the directional y vector. Okay, and so that's what it looks like in 2D space. Of course, this is what it would look like in 3D space. Okay, same concept. We're just adding, the direction of the vector according to the z-axis there, and that directional vector k. All right, so the last thing that we want to talk about here is the concept of horizontal and vertical components for a single vector. Okay, now to talk about this, I'm actually going to go to the next page a bit to give you this illustration here in Figure 6 and to kind of talk about it, and then we'll go back there. We see for a given vector v, we could always express this vector v, of course, if we're talking about 2D space here, in terms of its direction that it goes in the x direction, and the component of it, or the version or the portion of the vector that goes in the y direction, that makes it kind of go up from left to right, slanted like how it does. Okay, so here our point is that if I was able to break down my vector v into both its x direction and y direction components, we know that that could be expressed this way. Okay, we already know that because we've already established that. Okay, now the thing that I want to recall here is that notice that the parallelogram law is actually still being met here. Okay, it's just that my parallelogram is actually a rectangle and not necessarily something that's slanted. They're like, the slides are not slanted here. It doesn't look like this. It actually looks like a rectangle, or if these two numbers were the same, it would be a square. Okay, so it looks like that now. Okay, so we know that from trigonometry how we could get the actual length of this portion of the vector component that's on the x-axis is if I took the magnitude of this vector and multiplied it times cosine of this angle. Okay, and we know that to get this side, we would have to take the magnitude of this vector and multiply it times the sine of this angle. Okay, and that would be the same as this vector here, because it would have the same length and direction angle. So because of that, we now see here that Our magnitude for the x direction for that vector is just magnitude of v cosine of theta. And magnitude in the y direction is just that same magnitude, but sine of theta. And again, we recall that for in 2D, what the magnitude is going to be is just going to be, if we take the terminal point here for where this vector stops, and of course the initial point is assumed to be at the origin, then of course we're looking at v as being the component vector AB, which could also be interpreted as Vx, Vy. We could also look at it that way. But just in terms of AB, we just use these components here to do that. My point in saying all that is that I could also look at it this way. I could, this is not writing correct. I don't know why it's not doing that. All right, so let's try again. So this is Vx squared plus Vy squared. We could look at it that way, okay? But it's simpler for us to actually just look at it in terms of the terminal point, because a lot of times that will already be given to us. Our directional angle, again, we know that it's going to be in between 0 and 360, where we include 0 degrees, but not necessarily include 360 degrees, because we know 0 degrees and 360 are pretty much the same angle, okay? It's just you got one full rotation, whereas one has no rotation at all. So with that, I do want to mention here that I've only dealt with this concept of components both in the vertical and horizontal direction only because whenever we start to talk about 3D coordinate systems, the use of and how we actually define how we're going to calculate the magnitude of the z component can sometimes be tricky, okay? And depending upon the actual application that we're going to use the three-dimensional coordinate system for, sometimes it may not be needed, okay? So generally what I'm trying to say is that is out of the scope of this particular video. Now, it turns out that there are other three-dimensional coordinate systems like the spherical one, the cylindrical one, and polar coordinate systems that actually are made, well, part of the motivation for making them is to be able to say, all right, well, how are we going to deal with this z component, in particular the magnitude of it? And so in some instances, you know, like let's say like the polar coordinate system, you don't even need to worry about it. But for the spherical and cylindrical ones, you do need to worry about it, okay? And so it just really depends upon the application. So again, my main point here is that we're not going to worry about that now because that's something that you can learn later on to be specific whenever you deal with these different coordinate systems. However, what I do want you to understand is that there is a z component to a three-dimensional vector, and there are several different ways to be able to calculate the magnitude of that based upon what reference you want to use, okay? And so my point here is that I could figure out what's going to be the magnitude of a z component for a vector by finding that the angle in between the actual vector and the x-axis, the actual angle and the y-axis, that actual angle and the z-axis, okay? I could use any of those to do it. And since there's not one straight, standard way to do it based upon what coordinate system that you're in, we don't really talk about this standard way of doing it until we start to work in that particular coordinate system, okay? And so that's why I'm leaving that off for now, okay? All right, so This concludes this part 1 series of vectors. And so I've pretty much covered everything that we need to talk about from a conceptual and theoretical standpoint for us to be able to do example problems. So in the part 2 video that I'm going to do, I'll actually go over several examples of how we employ all these things that we've learned in this part 1 video. Hope to see you there. Take care.